Hello everybody, myself Prasanta Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. So in our last class of this subject, power electronics, we have discussed about the effect of source inductance on the performance of single phase and three phase converters. Today our topic of discussion will be effects of freewheeling diodes on the performance of converters, and how the techniques of power factor improvement can be employed in say phase controlled rectifiers. So let us start with effects of freewheeling diodes on performance of converters. Basically, many circuits, particularly those who are up or uncontrolled, include a diode across the load, and that is shown in the figure. And this diode is variously described as a commutating diode, or a flywheel diode, or bypass diode. And mostly we say it freewheeling diode. Basically, this diode is commonly described as a commutating diode or freewheeling diode, and its function is to commutate or transfer load current I from the rectifier whenever the load voltage goes into reverse state. These diodes serve two main functions. Two main functions, particularly. One is it prevents so particularly it prevents the reversal of load voltage except for small diode voltage drop. And secondly, it transfers the load current I from the main rectifier, thereby allowing all of its transistors to regain their blocking steps. So this is very important. The two functions mainly: it prevents reversal of load voltage except for small diode voltage drop, and secondly, it transfers the load current I from the main rectifier, and thereby allowing all of its transistors to regain their blocking steps. So in this figure 2, this is the figure 1, which is shown the positions of the commutating diode or freewheel diode. So this is DF. So this is load. This is connected across the load, and this is the phase control rectifier, and this is supply. Okay, this is the block diagram. Basically, in this diagram, where the freewheel diode or commutating diode is being placed, it is connected across the load. And this is the second circuit. This is a half-wave rectifier with a freewheeling diode. So that is shown here. This is a single thyristor is being used for a half-wave rectification purpose. It is a control rectifier because thyristor is used here. And this is the freewheel diode, which is connected across the RL load. Okay. So the load voltage and current waveforms are shown in figure 3, and with a diode DF thyristor will not be able to conduct beyond 180 degree. So this is the figure 3. This is actually output of outputs without freewheeling diode. Okay, this is actually just due to say RL load. So this due to the inductance effect. So this is the actually load voltage waveform like this. And when we are putting say freewheeling diode across the load, so waveform will be like this. This is output, and this is the load current. Okay, this is load current. Now this figure, actually this is in the waveforms of half-wave control rectifier with inductive load and freewheeling diodes. Basically, this portion actually shown in just only this part, this output load voltage and load current part, and this is described in here. So this is actually supply voltage. This is firing pulse given to the thyristor gate. This is load voltage. Okay, with the presence of the say freewheeling diode, and this is load current. Clear? This is load current. This is thyristor voltage. And what is voltage drop across the thyristors when it is in the blocking state? So this is this voltage. This is conducting state. This is the reverse blocking state, and this in this way. Okay. So actual waveforms are shown here. So so that the thyristor cannot conduct beyond 180 degree. So we know that during the positive half cycle, voltage is induced in the inductance, and now this induced voltage in inductance will change its polarity as the didt changes its sign, and diode freewheeling diode df will start conducting as soon as the induced voltage is of sufficient magnitude, and thereby enabling the inductance to discharge its stored energy into the resistance. So this is actually see. So when this will happen, so this inductance will change its sign. So during storing energy, it is positive, it is negative, and after that, when this portion actually when the negative voltage inputs, so this side will be reverse biased, and as a result, polarity of this didt will be changed, and it will be forward biased. And so energy will be dissipated through this path. Okay. So as a result, the output load voltage will be of this form with the presence of the df, that is shown once again. It is shown here. That is also described here. Okay. See these people. Here. So and accordingly the load current. Okay. So actually enabling the inductance to discharge its stored energy into the resistance. And so after 180 degree, the load current will freewheel through the diode, and the reverse voltage will appear across the thyristor that I told you. And the power flow from the input takes place only when the thyristor is conducting. And if there is no freewheeling diode during the negative portion of the supply voltage, thyristor returns the energy stored in the load inductance to the supply line, and with the diode df, the freewheeling action takes place, and no power will be returned to the source. So hence the ratio of the reactive power flow from the input to the total power consumed in the load is less for the phase control with a freewheeling diode, and in other words, the freewheeling diode inputs the input power factors. Okay, so that is shown. If you see, this is in absence of freewheeling diode. Okay, this is the load voltage, this is load current. So energy will be stored back. It will be like this. Okay, now in presence of power freewheeling diode, so this will be like this. Okay. And as a result, we can say this presence of freewheeling diode improve the power factors of the systems. Okay, mathematically, if I say this is actually EI sin phi divided by EI, this is equal to less, and sin phi also will be equal to less. As a result, since phi is less, power factor cos phi is more. Okay. So hence it is clear that freewheeling diode helps in improvement of the power factor of the system. Now what is the advantages? So advantages of the freewheeling diode in a full wave rectifier is like this. Freewheel diode at the output of a full wave rectifier will increase the DC voltage for a given firing angle due to elimination of negative portions of the instantaneous DC waveform in a SCR phase control converter. Secondly, will reduce the generated ripple on the DC side of a SCR phase control converter, and due to same reason as told in one, reducing the filtering requirements. And thirdly, will improve the input power factor in an SCR phase control converter due to ending the input current waveforms either by permitting internal freewheeling, say earlier by permitting internal freewheeling. So, however, the above will happen when only the DC side has sufficient inductance either as a filter or as a part of the load. And secondly, the firing angle is more than 30 degrees for three phase, and only after which the negative portion appears. So note that there will be no benefit in a diode rectifier since the freewheeling diode is always reverse biased. Okay, so other benefit is not there. So also to note, the use of freewheeling diode prevents operations of the SCR converter in inversion mode. So these are the say two advantages which has been sorted down from the technique of operations of the freewheeling diodes, and these advantages are summarized in this way. And that's I have discussed. Now we'll talk about the performance parameters of the converters. So basically, it is important to determine the performance parameter for different converters whose topologies can be single phase or multi-phase. And for that, the assumptions of devices are used are ideal, that is, they do not have any losses, and the devices have resistive loads. So if this is the thing, say this is load. Okay. So now DC voltage on load basically will be calculated like this. VDC equal to 1 by T 0 to TVL dt. So from this system, RMS voltage on load will be VL equal to root over of 1 by T 0 to T VL square dt. Form factor, that is VL by VDC, and a ripple factor that is root over of VL square minus VDC by VDC, that is form factors to root over of form factor square minus 1. And efficiency rectification factor, that is equal to theta equal to PDC by PL plus PD. PDC equal to like this, PDC equal to actually PDC equal to VDC into IDC, and PL equal to PL equal to your VL into IL, and PD equal to RT into IL square. Okay, so that's all actually. Then PD is the rectifier loss and RT is the resistance. So therefore we can write efficiency equal to VDC IDC by VL IL plus RD IL square. Okay, or that is IL square RD. That will be calculated like this: VDC square divided by VL square into 1 by 1 plus RD by RL. But actually, if we say if we say RD equal to 0, therefore this will be like this. Okay, the RD 0 means this portion will be like this. So VD by VL square, efficiency square, that is equal to 1 by form factors square. So transformer utilization factors, so that is equal to PDC by volt ampere ratings of the transformer, that is PDC by VAP plus VAS by 2. So VAP and VAS are the primary and the secondary power ratings of the transformer. So actually, this is about the external performance parameters for the effects for the converters. So this is the performance parameters of the converters, and we have discussed the effect of freewheeling diodes on the performance of the conductors, and in shortly we have summarized their advantages in short. Okay, so we can switch. Now we'll discuss about techniques of power factor improvement in the converters, and the main objective of this lesson is to how the different schemes of power factor improvement in the AC/DC converters are being done. And with these objectives, we'll discuss and we'll start the basic introductions. Is that after we have already discussed various types of AC to DC converters, that is control rectifiers, for both single and three-phase. Drop in the output voltage due to commutation overlap in the converters was also discussed in the because the inductance on the source side being taken into account. That also we have discussed in our earlier lessons, that is the effect of source inductance on the performance of single phase and three-phase converters. And in these sessions we'll discuss how the power factor improvement is done. So this is described here, and the three schemes for power factor improvement are discussed, and we'll discuss this. In all these cases, the circuit of a single phase full wave half control or semi control bridge converters, AC to DC, is used mostly as an example. So power factor improvement for phase control operation in both single phase and three phase half and full control bridge converters, that is single phase or single phase. We are discussing only single phase full wave half or full control bridge converters. The distortion factor or the power factor which is lagging decreases. Basically, as the average value of the output voltage VDC decreases with the increase in the firing angle delay, that is alpha. And this is also applicable for both three-phase half wave and full wave bridge converters also. And therefore, the three schemes used for power factor improvement basically used. One is extensile angle control, second is symmetrical angle control, and third is pulse width modulation control. In extension angle control, the circuit diagram of a single phase full wave half control force complicated bridge converter is shown. It is the this circuit. So single phase full wave half control or semi control bridge converter it is. So here this is the circuit diagram. Thyristors are being replaced by switches S1 and S2. Okay, this thyristor T1 and T2. See, that is told here T1 and T2 are replaced by switches, self-commutative devices such as power transistors or equivalent. Power transistor is turned on by applying a signal at the base and turned off by withdrawing the signal at the base. GTO, gate turn off transistors, can also be used, in which case it may be turned off by applying a negative short negative pulse to its gates, and is turned on by a short positive pulse like the thyristors. So in extension angle control, switch S1 is turned on at omega t equal to 0 and then turned off by force commutation at omega t equal to pi minus beta. Okay. The switch S2 is turned on at omega t equal to pi and then turned off at omega t equal to 2 pi twice pi minus beta. And the output voltage is controlled by varying the extension angle beta. So this is shown in figure B, that waveforms of output voltage, input voltage, input current, and current through thyristor switches is shown. And the fundamental component of the input current leads the input voltage, and the displacement factor, that is the power factor, is leading. So when this fundamental component of input current leads the input voltage, so power factor is leading. And this feature may be desirable to simulate capacitive load, thus compensating the line voltage drops. So this is shown here actually. Okay, so this is the circuit here, and this is the waveforms. See, it is from 0 to pi minus beta, then it is pi plus beta to 2 pi minus beta. This is actually output voltage waveform. This is input voltage waveform. This is actually thyristor current with the switch IT1. Okay, this is for IT2. Okay, this is for conduction and this is for conduction. Okay, that is this is for IT2. Okay, so basically this is actually load current here, IA. Okay, this is the load current. So, and this is the diode current, freewheeling diode. That is here. Okay, IDF. IDF like this, and because when this thyristor one, practically the thyristors are off, in that case the load current are fly away or freewheel through this freewheeling diode. That's why this is the function of the freewheeling diode current. And this is actually the value, average value. Okay. Actually, this is IA in this form. Okay. So this is load current actually, basically. Okay. This is minus IA. This is load current. And this is like this, the waveforms. Okay, this is for single phase force controlled semiconductor. So average output voltage we can found from the waveforms if we calculate it is 2 by 2 h by 0 to pi minus beta root 2 v sin omega to d omega t. So this will be like root 2 by pi v into 1 plus cos beta. And the value of VDC is varied from 2 root 2 by pi v to 0 as beta varies from 0 to pi. And the RMS value of the output voltage is that is equal to 2 by 2 h pi integration over 0 to pi minus beta 2 b square sin square omega t d omega t whole root. Okay, so that will be like this. So v equal to v into 1 by pi minus beta plus half into sin 2 beta whole root 2 whole root. Okay, so this scheme of extinction angle control can also be used for single phase full wave full control bridge converter with 4 switches instead of 2 needed in the earlier case. So that's about your extinction angle control. Second method is symmetrical angle control, and in this control can be applied for the same half control force commutated bridge converter with 2 switches S1 and S2. This is as shown in figure 1, and the switch S1 is turned on at omega t equal to pi minus beta by 2, and then turned up at pi omega t equal to pi plus beta by 2. The other switch S2 is turned on at 3 pi minus beta by 2, and then turned up at 3 pi plus beta by 2. So the output voltage is varied by varying this conduction angle beta, and the gate signals are generated by comparing half sine waves with DC signals as shown here. So this is the signal. Actually, in the second case, the conduction angle varies linearly with the DC signals, but in inverse ratio. So that is when the DC signal is 0, full conduction beta equal to pi takes place, and the DC signal being the same at the peak of the triangular reference signal. So no conduction that is beta equal to 0 takes place. And figure C shows the waveforms of the input voltage, output voltage, input current, and current to the switches, and the fundamental components of the input current is in phase with the input voltage, and the displacement factor is unity. Therefore, the power factor is input. So that is shown here. Okay. So this is like this. Clear? Okay. So this is the waveform, and this is your signal size range also like this. This is discussed here. Okay, in this portion. So there is a half sine wave can be obtained using a full generated by comparing triangular waves with a DC signal. and the second case the conduction angle varies linearly with the DC signal, but in the inverse ratio. It is shown here. Okay, so the average output voltage is like this: Vd is equal to 2 by pi integration pi minus beta by 2 to pi plus beta by 2 root 2 b sine omega t d omega t. That will come to 2 root 2 by pi b sine beta by 2, and the value of Vdc varies from 2 root 2 pi v to 0 as beta varies from pi to 0, and the RMS value of the output voltage is like this: V RMS is equal to 2 by 2 pi integration pi minus beta by 2 to pi plus beta by 2 to 2 b square sine square omega t d omega t, and then it is on root. So this will be b into 1 by pi beta plus sine beta root. Okay, so that is your extension, then symmetrical angle control. Actually, then we'll come to the next procedure of improvement, that is pulse width modulation control, PWM control. So if the output voltage of a single phase half control converter is controlled by a delay angle, extension angle or symmetrical, there is only one pulse per half cycle in the input current of the converter, and as a result the lowest order harmonic is third. So it is difficult to filter out the lower order harmonic current, and in pulse width modulation control, the converter switches voltages switches are turned on and off several times during a half cycle, and the output voltage is controlled by varying the width of the pulse. So the gate signals are generated by comparing a triangular with DC signal as shown in figure G. And in the case all these pulse widths obtained are equal, and figure E shows the input voltage, output voltage, and input current. The lowest order harmonic can be eliminated or reduced by selecting the number of pulses per half cycle, and however increasing the number of pulses would also increase the magnitude of the higher order harmonics, and which could easily be filtered out, and the earlier case of symmetrical angle control can be considered as a single pulse with modulation. That is shown here. Okay, so these are the say pulse width modulation techniques, waveforms. Okay, so this is a pulse rate. So this is pulse width modulation controlled waveforms. So details of output voltage and current inputs of the converters are given in this. And the output voltage, that is performance parameters, can be obtained in screw tapes by considering only one pair of pulses, such that actually say if one pulse starts at omega t equal to alpha 1 and ends at omega t equal to alpha 1 plus delta 1, the other pulse starts at omega t equal to pi plus alpha 1 and ends at pi plus alpha 1 plus delta 1. And then secondly, by combining the effects of all the pairs of pulses. So if mth pulse starts at omega t equal to alpha m and its width is delta m, del m, so the average output voltage due to p number of pulses is found like this: Vd is equal to summation of over m equal to 1 to p 2 by pi integration over alpha m to alpha m plus delta m, say root 2 b sine omega t d omega t, and so that will be root 2 b by pi summation of m equal to 1 to pi, so cos alpha m minus cos alpha m plus delta m. So if the load current with an average value of Ia is continuous and has negligible ripple, the instantaneous input current is expressed in the Fourier series like this. This expression can be like this: Is, this is the DC part, and this is the Fourier say AC part component. So due to symmetry of the input current waveforms, even harmonics are absent and IDC equal to 0, and the Fourier coefficients are obtained as like this. This is AN, okay, equal to 0, and this is Vn. Okay, So the equations of the IST is written as like this. So this is actually where phi n equal to tan inverse of am by bm equal to 0 and in equal to this. So various types of modifications in pulse width modulation techniques have been proposed, and one of the important method is sinusoidal pulse width modulation, pulse width modulation control method. And here the pulse widths are generated by comparing a triangular reference voltage VR of amplitude AR and frequency FR with a carrier half sinusoidal voltage VC of variable amplitude AC and frequency of 2fs. That is, the two sinusoidal voltage VC is in phase with the input voltage Vs and has twice the supply frequency Fs. So the widths of the pulses and the output voltage are varied by changing the amplitude of the reference, let's say, voltage, that is the amplitude of AR, or the modulation index M from 0 to 1. Okay. So the modulation index M is defined as it is the ratio of amplitude of the carrier signals and reference signals, that is carrier voltage and reference voltage. So that is equal to AC by ER. So, and maybe noted that the width of the pulses obtained are variable, and the widths are smaller at the center of the carrier signal, that is sinusoidal, and increases as one goes to start and end of the above signal. So this is shown in figure H, which shows the various waveforms including the currents through thyristors and the input current and the load current assumed to be continuous. It may be also noted that in RDFS multiple pulse width modulation control, the pulse widths are uniform, that is equal. So in this type of control, the displacement factor or power factor is unity and the power factor is input. The lower order harmonics one eliminated or reduced. For example, with 4 pulses per half cycle, and lowest order harmonic is the 5th, and so on. So that is lower order harmonics are eliminated, and different modifications have been suggested to take one such example. That is, if we take such ones as the pulse width one small in the center, that is shown in figure H, and the carrier signal is modified to take care of this. So the triangular waveforms are kept the same up to some point of the start and end of the cycle, and then the pulse widths can be made uniform. So the power factor is improved with various control methods we have discussed, and for different PWM methods used, the harmonic components of the voltage waveforms are also decreased or eliminated. So this is shown here. So this is actually reference signals. This is the carrier signals, and you say, so these are the this is pulse for thyristor 1. This is for 2. Okay, and this is the load current. Okay, this is supply current. This is plus I. This is minus I. This is I. So sinusoidal pulse width modulation control like this. So in this class or in this lessons we have seen the actually first of all we have discussed about the effects of freewheeling diodes on the performance of the converters, then different performance parameters we have discussed, and then we have discussed the techniques of the power factor improvements. We have mostly discussed 3 techniques, that is extinction angle control, then symmetrical angle control, and then pulse width modulation control. And we have also discussed one some modifications of the pulse width modulation control to improve the power factor, that is sinusoidal pulse width modulation control. So hope all of you have understood today's lessons, and if you have any difficulty So after reading, you may contact me, as I told you, and say uh, continuously I am telling you that we have taken the help of the textbooks what we have say written in our first class, and going on discussing on that, and also taken the different say NPTEL lectures and others materials available in the internet. So with this, I am ending this class today. Thank you all of you for listening, hearing.